Hi, good evening to all. Yes, today we are going to discuss about amines. Then after that, coordination compounds. Okay, first session will be amines. So we are going to do it. I think all of you are in a mode of preparation. You are in real tension now. So just we will complete amines in a very faster way. Okay, don't worry. Listen. So I think all of you can hear me, right? Are you there? Just text me here, okay? Yes. So we are starting the session. Amines is an important chapter in organic chemistry. So we are going to discuss important, very, very important objective sessions. Okay? You may get a real concept by completing this 16 or 18 questions. Okay? So we are going to do. First question. I will explain the concept behind it. Let me read the question. The reaction of ammonia with large excess of CH3Cl will give mainly. This is one of the method of preparation of amines. The portion is ammonolysis of alkyl halide. I'm just briefly explaining what is that. Then we will come back to that answer. Okay. So what is ammonolysis of alkyl halide? Yes. This is equal to, we can say, alkyl halide. This is alkyl halide. Okay. Yes, this is ammonia. We can say ammonia, NH3, right? This is alkyl halide. Yes. We can say alkyl halide, I can write this way, Rx, treating it with ammonia. Yes, this is NH3. So you can see HX is going out. In the first step, you will get RNH2. Yes, this is RNH2. This is a primary amine plus HX. This is the first step reaction. Then second step, what will happen? If you are taking excess alkyl halide, what will happen? Yes, if you are taking excess alkyl halide, this is the primary amine generated. That will react with one more molecule of alkyl halide. Yes, you can say Rx or RCl, whatever may be. So you will get HX is going out. You will get a secondary amine. Yes, you will get secondary amine. This is secondary amine. That secondary amine again reacts with alkyl halide. This is equal to this is primary amine. This is secondary amine. Secondary amine is here. This is secondary amine. Yes, RNHR again reacts with the alkyl halide. Yes, alkyl halide. Again H and X is going out. You will get tertiary amine. RNR again R, tertiary amine. Then tertiary amine again reacts with alkyl halide. See, tertiary amine has lone pair electron over here. Every amine has lone pair electron on nitrogen atom. So this will react with this will react again. Yes, this will react again with alkyl halide to form quaternary ammonium salt. How it will be? Yes, this is equal to tertiary amine. RN again R with lone pair electron reacts with reacts with, you can say, again alkyl halide. Yes, again alkyl halide, we can say it will reacts with again alkyl halide. Yes, you will get quaternary ammonium salt. You will get a quaternary ammonium salt like this, R, N, again R, using coordinate bond with R, and this will be converted into a quaternary ammonium salt. Okay, this will be converted into a quaternary ammonium salt. Remember, this is equal to Rx. You will be getting quaternary ammonium salt, right? Remember that. So final product of ammonolysis of alkyl halide is this one. You know how this is generated? Very simple. This is equal to lone pair. There is a lone pair electron on nitrogen over here. This lone pair will react with alkyl halide. This alkyl halide will ionize us as R plus and X minus. The R plus will react with the lone pair electron. R plus will make bond with the lone pair electron to form quaternary ammonium salt. So this is called ammonolysis of alkyl halide. So important point regarding this reaction, you have to remember, students, very simple thing. Ammonolysis of alkyl halide will give you mixture of amines along with the quaternary ammonium salt. So it's not a better method of preparing amines. Remember these two key points. Final product of ammonolysis of alkyl halide is quaternary ammonium salt. That is this one. This is equal to quaternary ammonium salt. Second point regarding this reaction, you are getting primary amine, secondary amine, tertiary amine along with the quaternary ammonium salt. So this is not a better method for preparing amines. So we can come back to this question. Anybody can tell me the answer now? The reaction of ammonia with a large excess of CH3Cl will give mainly. See, this is equal to quaternary ammonium salt. Here we called R4X minus. Here CH3 is equal to R. So CH3 4 times NCl minus. You will get like that. So this is your answer. So the first question answer, option is C, that is quaternary ammonium salt. I hope all of you got it right. So this is the first question. So remember, ammonolysis of alkyl halide, final product is quaternary ammonium salt. Okay. So moving to the next question. I think all of you got it right. Yes. So we are moving to the next question now. Can you read the question? This is also based on the previous point. Assertion. Ammonolysis of alkyl halide is not a suitable method for preparation of pure amines. What's your opinion? Tell me. Anybody can tell me. Ammonolysis of alkyl halide is not a suitable method for preparing primary amines. Yes, assertion is, we can say assertion is correct, right? Assertion is correct. Ammonolysis of alkyl halide is not a suitable method for preparing primary amine. Yes, no doubt about it, assertion is correct. Reason. Ammonolysis of alkyl halide yield mainly secondary amine. What's your opinion? Tell me fast. Yes, tell me. Ammonolysis of alkyl halide yield mainly secondary amine is wrong, because ammonolysis of alkyl halide you will get primary, secondary, tertiary along with the quaternary ammonium salt. So it is not a correct method. Okay, so ammonolysis of alkyl halide yield mainly secondary amine is wrong. So we can say assertion is correct, reason is wrong. Assertion true, reason wrong. Option is coming under C, right? Your option is C. That's it. So option is C. Assertion true, reason wrong. I think all of you got it right. Yes, please respond. Yes, Akshay, Hussein, are you okay? You got it? Yes, we are moving to the next question now, right? Yes, listen. So, listen. Ethylamine can be prepared by action of LiAlH4 on. See, ethylamine can be prepared by action of LiAlH4 on. Anybody can tell me the answer? Yes. Ethylamine. We want to get ethylamine. Ethylamine has 2 carbon atoms. We studied one reaction. This is equal to nitrile RC triple bond N. This is nitrile. On treating it with LiAlH4, we studied this reaction. LiAlH4. This is a reducing agent. Addition of hydrogen will occur here. This LiAlH4 will supply hydrogen, and hydrogen get added across carbon as well as nitrogen. After adding hydrogen here, you will get final product will be like that. You can say initial product, hydrogen get added here, again hydrogen get added, you will get RCH double bond NH, again hydrogen get added. Yes, again we are adding hydrogen, LiAlH4, final product will be like that, RCH2 NH2. So primary amine is obtained by reduction of nitrile. This compound is coming under nitrile family or cyanide family. So nitrile upon reduction with the LiAlH4, you will get primary amine. In short, you can do directly by reacting with LiAlH4, you can convert. Here you can say this carbon to hydrogen get added, this nitrogen to hydrogen get added, you will get RCH2NH2. This is an example of primary amine. Now coming back to the question. Yes, here you have CH3Cl, ethylamine. Ethylamine is obtained by reduction of this compound, nitrile, okay, because CH3CN upon reduction, you can say CH3CN on reduction with LiAlH4, you will get, which one, tell me, CH3CH2NH2. So this is called ethylamine. So ethylamine is obtained by reduction of CH3CN with the LiAlH4. This is a last year board exam question. Just go through it. Okay. Next one. Okay. Yes. I think all of you got it. We are moving to the next page. Okay. See the question now. Read the question fast. Which of the following would not be a good choice for reducing nitrobenzene to aniline? See, this is an important area. Sometimes they may ask another type question from this area. Sometimes they may ask direct question. This is a bit deviated question. So we will discuss. What is the concept behind it? I'm going to explain. Okay? Yes. So what is nitro compound? Yes, this is nitro compound, RNO2. We can convert nitro compound into primary amine. Remember, nitro compound can be converted into primary amine using reduction. Yes, reduction. Now the question is, which are the reducing agents used here? Yes, you have to specifically read that point in the reader, which all reducing agents are given. That you have to study properly. Which are the reducing agents used here? Yes. Number one reducing agent, you can use hydrogen bar catalyst. Hydrogen bar catalyst. That catalyst can be palladium, catalyst can be nickel, etc. So hydrogen bar nickel can use this here for this particular reduction. We can use hydrogen bar nickel, no doubt. We can use SN bar HCl. SN and HCl will react to generate hydrogen, and that hydrogen is used for reducing nitro compound into primary amine. Yes, we can use SN bar HCl, no doubt. See now, another one, Fe bar HCl. Yes, we can use Fe bar HCl also. We can use Fe bar HCl also. These are the three reducing agents given in the reader. Now we cannot use which one? Anybody can tell me? Yes, here we cannot use which one? They are asking which of the following would not be a good choice for reducing nitrobenzene to aniline. That is what? LiAlH4. LiAlH4. Shall I ask one question? Okay, so which of the following is not a good reducing agent for converting nitro compound to primary amine is LiAlH4. Anybody can tell me which is the best reducing agent out of these three? Please tell me fast. Which is the best reducing agent here? Anybody? Yes, I want your response. Tell me fast. Out of this, which is the best reducing agent? Waiting for your response. Yes. Very good. Okay, very good. Version is good. Okay, so it is equal to Fe bar HCl is better reducing agent. Tell me why. They will ask the board exam. That's an important area. Whenever you are studying a concept, study fully from it. Okay, so Fe bar HCl is the best reducing agent for converting. Fe bar HCl is the best reducing agent for converting nitro compound into primary amine. What is the reason? Yes, the reason I am telling, just remember this is also a very important point regarding this topic. So for converting nitro compound into primary amine, Fe bar HCl is the best reducing agent. Why? The reason, Fe will react with HCl to produce FeCl2 plus hydrogen, right? Hydrogen. This FeCl2, yes, FeCl2 will react with water. Water is the solvent there to get FeOH twice. You can say FeOH twice. FeOH twice plus HCl, right? HCl. So Fe will react with HCl to produce FeCl2 and hydrogen, and that FeCl2 will react with water. How came water over there? Yes, water will react with FeCl2. Water will react with FeCl2 to produce FeOH twice and HCl, and you can say FeOH twice and HCl will generate. Here HCl is regenerated. Here as a byproduct you are getting HCl. Means HCl is regenerated again. So here we can use initial amount of HCl, we can do the reduction with the initial amount of HCl. After that, you don't need to add HCl again and again. Here HCl is regenerated, so we can do reduction with a less amount of HCl. Economically it is good. That is why Fe bar HCl is a better reducing agent. That also is coming in the exam. Just go through the portion. It's very, very important area. Repeating, which is a best reducing agent for converting nitro compound into primary amine? Yes, the answer is Fe bar HCl, because in this reaction HCl is regenerated, so we can do the reduction with a less amount of HCl. Okay, so just go through it. This is a method. The worst reducing agent is LiAlH4. We can't use LiAlH4 here. LiAlH4 cannot convert nitro compound into primary amine. This is also a last year board exam question. Okay, so we are moving to the next question. I hope all of you got it, right? Yes. Next one. See the question. CH3CONH2 on reaction with NaOH and bromine in alcoholic medium gives. Anybody can tell me? This is an easy question. This is a familiar reaction. Anybody can tell me the answer fast? Yes, anybody can tell me the answer fast? Tell me. I'm waiting for your response. Okay, listen now. So CH3CONH2, I'm just giving a small idea. After that, we'll come back to this question. Okay, listen. Yeah, Hofmann's bromamide reaction. Very good. This is Hofmann's bromamide reaction. I'm giving a small idea. Just wait. So this is equal to, just remember this. You have to remember this. This is carboxylic acid. Okay, carboxylic acid. Carboxylic acid. We know that. On heating with ammonia, yes, on heating it with ammonia, you will get RC double bond NH2. Okay, strong heating, you will get acid amide. This is called acid amide. Okay, acid amide. You have to study this. This chart, you have to study. It will be very useful for you. This is carboxylic acid. Heating with ammonia, you will get RC double bond NH2. This is equal to acid amide, no doubt. Now this acid amide can be converted to primary amine in two different methods. Which are the two different methods? Yes. Number one method I am talking. Number one method is on treating it with LiAlH4, you will get a primary amine. That will be RCH2NH2. You will get a primary amine with the same number carbon here. See, number of carbon here and number of carbon same here. This is primary amine with the same number carbon. Same number carbon. Okay. Now, if I am treating it with the bromine bar NaOH or bromine bar KOH. Yes, if I am treating it with the bromine bar NaOH. Yes, listen. Bromine bar NaOH or bromine bar KOH or NaOBr. These are the agents representing Hofmann's bromamide reaction. Whenever you are treating this acid amide with bromine bar NaOH or bromine bar KOH or NaOBr or KOBr, you will get a primary amine with one carbon less. Here you can remove, simple way, you can remove the C double bond from here. Okay. If you are using this reaction, you can remove the C double bond. You can connect this R, you can connect this NH2 together. Remove CO. Connect R and NH2 together. See, very simple. If you are using bromine bar NaOH or bromine bar KOH, the answer is so simple. Just remove CO, connect R and NH2. You will get a primary amine with a one carbon less. This is primary amine with a one carbon less. Now coming back to this question. This is the two difference. Just go through it. Okay. Yes. What's the difference here? Now tell me. CH3CONH2 on reaction with NaOH and bromine in alcoholic medium gives, we can remove the CO. After removing the CO, you will get which one? Option B, right? Go through it. It's very important. You have to study the name reaction with the full balanced equation. It's very, very important. Okay, so this is CH3NH2. So this will be the answer, right? I hope all of you got it, right? Yes. So we are moving to the next question. Listen now. Among the following amines, which one expected to be the lowest boiling point? Tell me the answer. I want the answer from your side. which one expected to be the lowest boiling point? Most of the students are making mistake here. 100% sure you will make mistake here. See, what is the rule of deciding boiling point of amines? Tell me. I want your participation. Yes? Akshay, tell me. Yes. So actually the boiling point of amines, there is a rule over here. Okay. So with a different number carbon, what's the rule? With the same number carbon, what's the rule? You have to select. Okay. So with the different number carbon, suppose amines have different number carbon, what to do? With the different number carbon, we will go for molar mass. With the different number carbon, high molar mass, we can say high molar mass, high boiling point. This is the rule with the different number carbon. Less molar mass, we can say less boiling point. This is the rule with the different number carbon. Okay. So with the different number carbon, if amines have different number carbon, you have to go this rule, high molar mass, high boiling point, or more number carbon, high boiling point, less number carbon, less boiling point. That's the logic. With the same number carbon, what to do? Yes, with the same number carbon, what's the answer? Now tell me. With the same number carbon, the order of boiling point is primary, secondary, tertiary. This is the order of boiling point with the same number carbon. This is a key point. Remember, note down. So, with the different number carbon, we will check the molar mass. Molar mass, more means more van der Waals forces, more attractive force, and high boiling point. We can say with the same number carbon, we will check whether it is primary, secondary, tertiary. See, primary amine can form more number hydrogen bond compared to secondary, and tertiary amine can form less number of hydrogen bond. See, boiling point depends upon the attractive force between the molecule. If molecule can form more number hydrogen bond, the attractive force between one molecule and other molecule becomes stronger. Think like that. You are sitting in the class by holding hands each other. So your friend is going to evaporate. So you all will pull them back. Don't go, we are here. Don't go, we can go together. That is some sort of attractive force is there. That type of bond is there here. Hydrogen bond is more for primary amine. Primary amine can form more number of hydrogen bonds because hydrogen number is more here. It can form more number of intermolecular hydrogen bonds. So primary amine will have high boiling point provided number of carbon atom is same. When number of carbon atom is different, we will count the molar mass or we will count the number of carbon and decide the boiling point. See, coming back to this question, I think all of you got it, right? With the same number carbon, primary has high boiling point, then secondary, then tertiary. With a different number carbon, less carbon will have less boiling point, more carbon will have more boiling point. Can you tell me the answer for here? Tell me. Among the following amine, which one expected to have lowest boiling point? Anybody? Tell me the answer fast. Yes, this one. Most of them have wrong concept. Yes, sir, primary amine has high boiling point. No, primary amine, methylamine is small carbon atom only. Even though it is primary, its boiling point is less because the different number carbon atoms are there. These amines have different number carbon. When carbon atoms are different, go for this rule. When carbon atoms are same, go for this rule. Okay? So the answer is what? Methylamine. This is also a last year board exam question. Remember, most of the students will make mistake here. So primary has high boiling point, secondary has less boiling point, tertiary has less boiling point. That rule is possible only if you have same number of carbon atom. Got it? Yes. Next one we are talking. Okay. Yes, students. So the next question. Now you can tell this. Can you tell me this answer fast? Yes. Can you tell me this answer? Arrange the following in the increasing order of boiling point. You have butanamine. You have N-dimethyl butanamine. You have N-ethyl ethanamine. So let us write the structure. So see, students, whenever you are doing objective question, don't be in a rush. You keep quiet and write everything on a paper and do, because sometimes in a hurry you'll make mistake. So we will do now. In board exam you are getting enough time. So this session is only for board exam. Okay, wait. So how to do? Butanamine. What is butanamine? 4 carbon atom amine. This is 4 carbon atom amine. Okay, this is equal to butanamine. CH3, CH2, 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 NH2. This is equal to butan 1 amine. They didn't mention butan 1 amine. Yes, it's butan 1 amine. Okay. Then what is N-ethyl ethanamine? Yes, ethanamine means CH3, CH2, NH. N-ethyl indicates ethyl group is connected to nitrogen. Yes, this is nitrogen. Ethyl group is connected to nitrogen. This is equal to N-ethyl ethanamine. Then what is this? N-dimethyl ethanamine? Yes, ethanamine is CH3, CH2 with N. N-dimethyl means all 3 hydrogen atoms are replaced by what? Methyl group. See, this is equal to N-dimethyl methanamine. Now, can you tell me the answer easy? This is coming under primary. Yes, this is coming under primary, no doubt. This is coming under secondary. Yes, this is coming under tertiary. Check the number of carbon atom. See, check the number of carbon atom. Tell me the answer first. Check the number of carbon atom. Number of carbon atom here it is 4. Number of carbon atom here also 4. Number of carbon atom here also 4. See, when number of carbon atom is same, what's the order of boiling point? Primary will have more boiling point, then secondary, then tertiary. Because primary can form more number of hydrogen bond, intermolecular hydrogen bond. Okay, so primary more, secondary, tertiary. What will be the answer here? Yes. Here butan 1 amine A. A will have high boiling point, then C, then D, then B, right? A will have high boiling point, no doubt. A has high boiling point, then secondary, then tertiary. So option D is your answer. Now one more thing. Students, how to decide primary, secondary, tertiary from the name itself. Even you don't need to write the structure. From the name itself, you can understand primary, secondary, tertiary. How? So simple logic. Listen. Okay, simple shortcut. No need of writing structure. Wait. See how to identify primary, secondary, tertiary from the name itself. See, this is butan. I can tell this way. This is equal to butanamine. Butanamine has no capital N. No capital N. No capital N in the name. N-ethyl ethanamine has 1 capital N. 1 capital N. Okay. Now N-dimethyl ethanamine. N-dimethyl ethanamine has 2 capital N's, right? 2 capital N. 2N. If you have no N, that is primary. If you have 1 N, it is secondary. If you have 2 N, that is tertiary. Easy to identify primary, secondary, tertiary from the IUPAC name. If you have no capital N, it is primary. If you have 2 capital N, it is tertiary. If you have 1 capital N, it is equal to secondary. Remember. So no need of writing structure even. You can do it. I hope all of you got it, right? Yes or no? Now we are moving to the next question, right? Okay. See now, which of the following is least basic? Students, do you know about basic nature of amines? We studied why amines are basic in nature. What is the order of basicity? See students, you have to understand a lot from the basic nature. 100% every time board exam is asking this area, you will get 1 question from basic nature. But you have to understand the clear concept of basic nature. Let me discuss a shorter way. Okay. We know that the order of basic nature in shorter way I am talking. Okay. What is the order of basic nature? Listen. Order of basic nature of different amines. There are so many medium. Gaseous medium, aqueous medium, so many medium. What is the order of basic nature? If you know this shortcut method, you can predict the order of basic nature in an easy way. So easy. Wait. What is the method? Yes. Order of basic nature of aliphatic amines are like that. Primary, then secondary, then tertiary. Then I am writing primary, tertiary, secondary. Then I am writing tertiary, primary, secondary. These are all aliphatic amines. These are all aliphatic amines. Okay, aliphatic amines. Okay, this is a order of basic nature in gaseous medium. This is in gaseous medium. Okay, and this is the order of basic nature in aqueous medium. This is the order of basic nature in aqueous medium for aliphatic amines. This is the order of basic nature for aqueous medium for methyl group amines. For methyl amines. For methyl amines. For methyl amines. This is the order of basic nature for aqueous medium for methyl amines. There are so many reasons over here. We will discuss. Wait. And this is the order of basic nature of aliphatic amines. Okay. Aliphatic amines, order of basic nature is like that. Then after aliphatic amines, ammonia is coming. Ammonia. Aliphatic amines are more basic than ammonia. All aliphatic amines are more basic than ammonia. No doubt. I will tell you why. This is aliphatic amines. They are more basic than ammonia. Then who will come? Aromatic amines will come. Aromatic amines. Aromatic amines. Okay, so this is the chart you have to remember to know the order of basic nature. Aliphatic amines in gaseous medium, this is the order. In aqueous medium, this is the order. In aqueous medium for methylamine, this is the order. So you have to remember this order. Now you will be getting the answer. There are reasons. We will discuss one more topic. We will do weight. So let me do this answer now. Very simple way. Without checking the reason, I can do the answer. Tell me, which of the following is least basic? These are all, yeah. How to identify aliphatic amine? Aliphatic amine contain methyl group, ethyl group, like that, propyl group, like that. Aromatic amines, amino group is directly connected to the benzene ring. So how to decide aromatic amine? Yes, this is an aromatic amine. Tell me why this is aromatic amine. Why? Because amino group is connected directly to the benzene ring. C6H5 is benzene ring. So amino group is directly connected to the benzene ring. That is aromatic. This is aliphatic tertiary. Okay. This is ammonia. This is aliphatic secondary. Now, they are not asking any medium. See, you are in confusion. They are not asking any medium. When no medium is given, go for aqueous medium. Okay, suppose they are not specifying any medium. Your answer, you have to go for aqueous medium. Out of this, they are not asking which is most basic. They are asking which is least basic. Least basic is what? Aromatic amine. Okay, aromatic amine is the least basic one. Got it? So here, which of the following is least basic? You can see this chart. Aromatic amines, ammonia, aliphatic, gaseous medium, this is the order. Aqueous medium, all amines other than methylamine, this is the order. For methylamine, this is the order. So you have to remember this. This is the order of basic nature for different amines. All of you got it? Yes or no? Tell me fast. Yes? Christopher, tell. Are you okay? Yeah. Now we are telling what is the reason behind it. Okay. What is the reason behind gaseous medium, aqueous medium and everything? We will discuss factors affecting basicity. That's very, very important. Okay. So we are moving to do the next question. There I will explain the factor affecting this gaseous medium, aqueous medium and methylamine. You have to study this order. Go back and read it. Okay. So we are moving to the next question. Wait. Now, listen. Here, reasons I will tell you. Let me discuss this question. This also you can do easily with this order. Wait. See now. Kb value directly proportional to basic nature. Kb value directly proportional to basic nature. pKb value inversely proportional to basic nature. pKb value inversely proportional to basic nature. This is a logic you have to remember. Sometimes They may ask like that also. So Kb value inversely directly proportional to basic nature. Pkb value inversely proportional to basic nature. And groups with plus I effect, increases basic nature. Okay, groups with plus I effect increases basic nature. Got it? Groups with minus I effect, decreases basic nature. This is a general rule. So Kb value directly proportional to basic nature. Pkb value inversely proportional to basic nature. Groups with plus I effect groups. Examples are, which are the groups with plus I effect? Tell me. Alkyl groups. Alkyl groups are groups with plus I effect. Okay, alkyl groups increases basic nature. Groups with minus I effect means NO2. We studied it last class. NO2, then fluorine, chlorine, bromine, iodine, CN, etc. decreases basic nature. This all will decrease basic nature. This all will increase basic nature. Kb directly proportional to basic nature. Pkb inversely proportional to basic nature. Remember this. Okay. So coming back to the question now. Now you can do this. Okay, listen. How to do this question? Tell me. Listen. What's the method? Which of the following has lowest pKb value? Lowest pKb value indicates what? See students, lowest pKb value. Lowest pKb means more basic. Lowest pKb means more basic nature. Okay. Lowest pKb indicates more basic. Now tell me which of the following, they are asking indirectly, which of the following is more basic. We can check. One by one we can check, right? Which of the following is more basic? One by one. First one, there is NO2 group. This is aromatic. This is also not amine. This is equal to acid amide. This is acid amide. Not an amine. This is aromatic. This is not aromatic, aliphatic. Why aliphatic? Because NH2 group is connected to the side chain. NH2 group connected to the side chain is not considered as aromatic amine. That's a key point. NH2 group connected to the side chain is not an aromatic amine. It is coming under aliphatic amine, right? So NH2 group connected to the side chain is not aromatic. Aromatic amines are the amines where NH2 group or amino group is directly connected to the benzene ring. So here this is less basic because of NO2. This is aromatic. Aromatic amines are less basic. Acid amines are not purely basic. They are amphoteric in nature. They show both acidic and basic nature. They are not coming into the picture at all. These acid amides are not coming into the picture. So out of that, which one is most basic here? The most basic is aliphatic here. This is the most basic one. And most basic substance will have lowest, we can say, pKb value. Lowest pKb value is for the one with the high basic nature. Okay. So high basic nature here it is what? CH3NH2. Okay, means benzene ring with the CH2NH2. Hope all of you got it, right? Yes, that's it. So remember, whenever you are attending a question based on basic nature, you have to understand clearly which is aromatic, which is not aromatic. Here this is aromatic because connected directly to the benzene ring. Aromatic because NH2 connected directly to the benzene ring. And this is not completely aromatic. We can say NH2 is on the side chain. So this will be more basic than all others. Okay. Yes. I think all of you got it, right? Yes or no? Students respond. Yes. So we are moving to the next question, right? Yes. This is factors affecting basic nature. That you have to remember, students. So many things are there. I will try my best. Time is very less. Okay. So given below two statements are assertion and reason. Assertion. Tertiary amines are more basic than corresponding secondary amine and primary amine in gaseous state. No doubt. Correct. Tertiary amines are more basic than corresponding secondary and primary amine in gaseous state. Yes, correct. You know the order of basic nature in gaseous medium. We already know. Just I am revising. This is the order of aliphatic amines in basic nature. See, the order is like that. tertiary, then secondary, then primary. This is called gaseous medium, then primary, tertiary, secondary in aqueous medium. Okay, what is the reason? I am going to tell you. The reason is that, here reason why gaseous medium, which is a factor affecting the basic nature in gaseous medium, is only one thing, plus I effect. Plus I effect means electron donating group increases basic nature. Okay, increases basic nature. So only one effect is dominating, only one effect is observed in gaseous medium. Gaseous medium basic nature is decided by plus I effect only. There is no other effect, because more electron donating group, more basic nature. More carbon atom, more basic nature. Tertiary has more electron donation from different ends, so it will have more basic nature. So this is the reason why gaseous medium order of basicity is like that. Okay, aqueous medium, what is the reason? See, aqueous medium, there are two reasons. Wait, number one reason, the protonated amine formed is stabilized by hydrogen bonding. Stabilization of protonated amine by hydrogen bonding. One reason is that stabilization of protonated amine, stabilization of protonated amine by hydrogen bonding, okay, stabilization of protonated amine by hydrogen bonding. Second reason is that you can say less steric hindrance. Okay, this is the two reason why aqueous medium basic nature is decided by inductivity is also there, but this is more basic, secondary is more basic because of these two advantage, stabilization of protonated amine by hydrogen bonding. So this amine, you studied in CBSE reader, amine can undergo protonation. After protonation, you will get protonated amine. This is equal to amine. Yes, this is equal to amine, RNH2. Upon protonation, you will get protonated amine. This protonated amine is stabilized by hydrogen bonding. That's the reason secondary amine is more basic by considering dissolve effect. Stabilization of protonated amine by hydrogen bonding and less steric hindrance. What is steric hindrance? During hydrogen bonding, the hindrance is, the bulky groups are less for primary and secondary. So primary and secondary expected to have high basic nature in aqueous medium, but altogether effect is coming this way, primary, tertiary, secondary. Remember, okay? So three factors affecting the basic nature is inductive effect. Only inductive effect is playing an important role in gaseous medium, and all three effect, inductive effect as well as steric effect as well as stabilization of protonated amine in aqueous medium, that all plays an important role in basic nature in aqueous medium. So aqueous medium, there are three factors, inductive effect also, stabilization of protonated amine, that also, then less steric effect also. These are the three effects. We have less time to explain more, just I am going back to the question. Okay, see, given below two statements are assertion and reason. Assertion, tertiary amines are more basic than corresponding secondary and primary amine in gaseous state. Assertion is correct. In gaseous state, tertiary amines are more basic, no doubt. Tertiary amines have three alkyl group which cause plus I effect. Yes, that is correct. Tertiary amines are more basic. See the reason in gaseous medium. Reason in gaseous medium is plus I effect. See students here, gaseous medium basic nature is based on only plus I effect, no other effect. So gaseous medium, tertiary amines are more basic due to plus I effect. So assertion correct, reason correct, correct explanation. Okay, assertion correct, reason correct, correct explanation. Go through it. It's a last year board exam question. Remember. So tertiary amines are more basic than corresponding secondary and primary. Yes, correct. It is because of plus I effect. Tertiary amine contain more number of alkyl group which can produce more plus I effect. Okay, that's it. The next one we are talking. I hope all of you got it. Yes. So we are moving to the next question. Okay. See now, this is one more question from basic nature, then only I can complete that concept clear. So C2H5 twice NH is more basic than C2H5 thrice N in aqueous solution. See, in aqueous solution, order of basic nature is secondary, tertiary, primary. This is the order of basic nature in aqueous solution. Aqueous solution. Yes, correct. This statement is correct. You can see this is secondary. Yes, this amine is secondary, no doubt. This amine is tertiary. Yes, this amine is tertiary. So secondary is more basic than tertiary in aqueous solution. Correct? Assertion correct. So secondary is more basic than tertiary in aqueous solution. No doubt it's correct. The reason. Protonated amine formed by secondary, this is secondary, is more stabilized by hydrogen bonding. Yes, no doubt. And there is less steric hindrance. Yes, reason also correct. So secondary amine, protonated amine formed by secondary amine is more stabilized by hydrogen bonding. Okay, that's the reason we can say more stabilized by hydrogen bonding. So that's the reason. So because more it has less steric hindrance. So assertion correct, reason correct, correct explanation. So option is A, assertion correct, reason correct, correct explanation. Okay, go through it. Student, do you want the hydrogen bond stabilization? If you want, you can request, I will explain, otherwise I can skip the question. Are you okay? You got it? Please respond fast. Okay, so we can move to the next question, right? Yes. So this is just go through this area. This is little important. They are going to ask this. Okay. Next one. Which of the following agents, which of the following reagents used for Hinsberg test of amines? Students, you know what is Hinsberg test of amines? Which of the following used for Hinsberg test? Anybody can tell me the answer. What is Hinsberg reagent? We studied Hinsberg reagent. What is Hinsberg reagent? Yes, Hinsberg reagent is, you can say Hinsberg reagent is benzene sulfonyl chloride, benzene ring with the SO2Cl, benzene ring with SO2Cl, or we can write it as C6H5SO2Cl. We know that this is equal to Hinsberg reagent. Okay, so primary amine plus Hinsberg reagent, you will get a precipitate soluble in NaOH. We studied before. Then secondary amine plus Hinsberg reagent, you will get a precipitate insoluble in NaOH. Now tertiary amine plus Hinsberg reagent, no reaction. You have to go and check the equations and everything. This is a capsule form you have to study. So Hinsberg reagent is benzene sulfonyl chloride, benzene ring with SO2Cl, C6H5SO2Cl, and Hinsberg reagent is used for chemical test to distinguish primary, secondary, tertiary amine. So primary amine plus Hinsberg reagent, you get a precipitate soluble in NaOH. Secondary amine plus Hinsberg reagent, you get a precipitate insoluble in NaOH. Tertiary amine plus Hinsberg reagent, no reaction. Coming back to this question, tell me what's the answer. Which of the following reagent is used as Hinsberg reagent? Very simple question, option D. Okay, Hinsberg reagent is C6H5SO2Cl. Name is benzene sulfonyl chloride. Are you okay, students? So we're moving to the next question, right? Yes. I think all of you are okay, right? Yeah. So next question. This is very, very important reaction, students. Anybody can tell me what's the reaction over here? It's a primary amine treating with alcoholic KOH and chloroform. What is the reaction? Anybody can tell me the name of the reaction? Anybody, please? Yes, I am waiting for your response. Tell me. Yes. Good. So it's what? Tell me. Carbylamine reaction, right? Yes, this is primary amine plus alcoholic KOH. This is equal to primary amine. On treating it with a chloroform CHCl3 plus KOH, you will get RNC isocyanate, foul smelling isocyanate, plus you can say KCl plus H2O. Okay, KCl plus H2O. This is a reaction. So primary amine plus chloroform plus alcoholic KOH, you will get isocyanate plus KCl and H2O. Isocyanate is poisonous. Some of the isocyanates are highly poisonous. You can't perform this one in the lab. You won't be there. And moreover, so this is having a foul smelling substance. Okay. So this is called carbylamine test. Only primary amine will give carbylamine test. This is primary amine that will give carbylamine test. Now coming back to the question. C6H5NH2CHCl3A. What is A? They are asking what is A. Actually, if you are balancing, it will be 3KOH, 3KCl and 3H2O. If you are balancing, it will be like that. 3KOH, 3KCl and 3H2O. This is the A. So compound A equal to isocyanate. Compound A equal to C6H5NC, right? The compound A over here, it is equal to C6H5NC, that is isocyanate. This is a chemical test to distinguish primary amine from other organic compound. Only primary amine will give carbylamine test. Okay, so the next one we are talking. Are you okay? Yes, the next one. See now, this is very important area, amino group. Okay, amino group is orthoparadiaretic and is electrophilic substitution reaction. Amino group is orthoparadiaretic in electrophilic substitution. Students, yes, correct. This is amino group. This is aniline. This is aniline. Aniline is highly activating as well as highly activating towards ring substitution. It is orthoparadiaretic. Correct. It is orthoparadiaretic. We know that. Right? Aniline is orthoparadiaretic, no doubt. Aniline is orthoparadiaretic because it shows plus R effect. Plus R effect is a reason for orthoparadiaretic. You learned before in 11th standard also, in 12th also. So aniline is orthoparadiaretic, no doubt. Aniline is orthoparadiaretic towards electrophilic substitution reaction, no doubt. Aniline cannot undergo Friedel-Crafts reaction. Yes or no? Yes, that also correct. Aniline cannot undergo Friedel-Crafts reaction. They may ask reason why. Yes, this aniline, we can say, in Friedel-Crafts reaction, we are using which compound? Yes, we are using a catalyst, namely AlCl3. Okay, this is CH3Cl in presence of AlCl3. The problem with AlCl3 is that AlCl3 is electron deficient compound. Last class we discussed AlCl3 can attack the carbonyl oxygen. We discussed before. This AlCl3 is electron deficient compound. The AlCl3 is coming from a club called Lewis acid. Is a member of Lewis acid club. He is so electron deficient. He is crazy towards electron. So what happened? This aluminum chloride is there. Aluminum chloride is electron deficient compound. It will form, salt with aniline. So that is why this is basic in nature. This is basic. Aniline is basic in nature. This is acidic in nature. They together will form salt with each other. So aniline cannot undergo Friedel-Crafts reaction. Remember, that's a key point. That's very important. They may ask why aniline cannot undergo Friedel-Crafts reaction, because aniline is basic in nature. AlCl3 is a Lewis acid. They form salt with each other. They will combine to form a salt this way. They will combine to form a salt this way. We can say this is NH2AlCl3 minus and plus. This is the salt generated between aniline and aluminum chloride. Because of that, it will not undergo Friedel-Crafts reaction. So we will come back to the question now. See now, aniline is orthoparadiaretic. Yes, no doubt. Aniline cannot undergo Friedel-Crafts reaction. That also correct. So here, assertion correct, reason correct, not the correct explanation. So option is B. Assertion is correct, reason is correct, not the correct explanation. So option is B, right? I think all of you got it. Remember, student, these questions are really important. This Friedel-Crafts why aniline cannot undergo Friedel-Crafts reaction? That's a repeated question. Go through it. Okay, so we are moving to the next question. Is it okay? Yes? Tell me fast. Okay, so we are moving to the next question. Okay, good. See now, next one, assertion. Now, acetylation of aniline gives mono-substituted product. This is a last year board exam question. Acetylation of aniline gives mono-substituted product. Yes, what is acetylation? Some of them are looking up only. What is acetylation? Tell me. Yes, I will tell you. This is aniline. Okay, this is aniline. Aniline is highly reactive. We know that. Aniline is highly reactive, right? Aniline is highly reactive. This is aniline. Is highly reactive, highly activating towards ring substitution reaction. See student, aniline is highly activating towards ring substitution reaction. Highly activating means hyperactive. Think like that, it will be more reactive than benzene. Okay, it's highly activating. We can reduce the activating nature of aniline using acylation reaction. What is acylation reaction? Yes, we can say, what is acylation reaction we are discussing? It will react with the acid chloride, CH3COCl. Or I can say it will react with the CH3 C double bond OCl. Or it will react with the acid anhydride, CH3CO twice O. This H and Cl is going out. After that you will get acetylated product. You will get NHCO CH3 or NHC double bond or CH3. Yes, this is correct. Acylation of aniline giving mono substitute product is correct. It is giving mono substitute product. Mono means one hydrogen is replaced by COCH3. Yes, correct. So that assertion is correct. Now second one. Activating effect of NHCOCH3 group is more than that of amino group. Tell me what's your opinion. Activating effect of NHCOCH3 is more than that of amino group. See in CBSE we studied aniline, simple example I am talking. Aniline upon bromination, direct bromination, you will get 2,4,6 tribromoaniline because aniline is highly activating. We can reduce the activating nature. We can reduce the reactivity of aniline towards ring substitution reaction by doing acylation. This compound generated is called acetanilide. This compound is called acetanilide. Okay, acetanilide or N-phenyl ethanamide. N-phenyl ethanamide. This compound is less reactive than aniline towards ring substitution reaction. So by acylation, we can reduce the activating nature. We can reduce the activating nature. Okay, reduce the activating nature. How it is reducing activating nature? Yes, I will tell you. This is equal to aniline. Yes, this aniline you have NH here, NH, C double bond. This is acetanilide. Yes, this acetanilide has lone pair electron on nitrogen. There is a double bond over here. This lone pair and double bond are in conjugation. Conjugation means they are separated by a single bond. So they can engage in resonance. Because of that, lone pair is not available here. When you have no lone pair here, the activating nature is reduced by absence of lone pair. In aniline, lone pair is available, and during resonating structure, this lone pair is shifting to the ring, so that the ring will get activated over there. So here activating nature is reduced upon acylation. So for the being time, you remember, activating nature of aniline is reduced by acylation. So the answer is activating effect of NHCOCH3 group is more than that of amino group. Wrong. So actually activating nature of NHCOCH3 is not as than aniline, not that much as aniline. No, it is less than aniline, because we are reducing the reactivity of aniline by performing acylation. So assertion is correct, reason is wrong. Assertion is correct, reason is wrong. Assertion true, reason wrong. This is a bit harder Remember student, this was a board exam question. Remember, they are asking that level questions. Okay, remember. Okay, so we are moving to the next question. I think all of you got it, right? Yes, it's a bit harder one. Just go through it. Okay. Now, we are moving to the next question. See now, even though this is very important question, students, very, very important, repeatedly coming in the board exam. We selected such questions only. You can go and check the previous board exam papers. The concept is coming in board exam. Even though NH2 group is ortho-para-directing, in electrophilic substitution reaction involves bromination, nitration, like that, okay, sulfonation, like that. So, even though aniline is ortho-para-directing towards ring substitution reaction or electrophilic substitution reaction, aniline upon nitration gives some amount of meta-nitroaniline. Yes, this is given in the reader. This is aniline. Upon nitration, direct nitration, concentrated HNO3, concentrated H2SO4, you will get orthonitroaniline. Yes, you will get paranitroaniline. Yes, you will get paranitroaniline. Yes, you will get metanitroaniline. Yes, that is correct. So aniline will give some amount of metanitroaniline. How much? This will be 51%. This will be 47%. This will be 2%. See now, metanitroaniline you are getting around 47%. Now we are surprised why aniline is giving metanitroaniline. Aniline is ortho-para-directing, but aniline is giving metanitroaniline. Why? Yes, listen now. So aniline is giving metanitroaniline upon nitration. Why? The reason I am talking, that's an important concept, students. You have to go through the reader. Okay, see. So aniline upon whenever we are using nitrate mixture, this is equal to aniline. Aniline has lone pair here. Aniline is a base. Okay. In nitrate mixture, this is acidic. This nitrate mixture is acidic in nature. This is acidic. So they can donate H+. Acidic substance will furnish H+. Okay. So acidic substance can give H+ ion. So from this mixture, you will get H+ ion. So H+ ions got divorced from here and there, roaming around here and there. H+ ions will be finding happy with this lone pair electron. It will undergo protonation here. So H+ ion will make bond with NH2 and you will get a compound, namely anilinium ion. What is the ion? Anilinium ion, NH3+. This is equal to anilinium ion. This compound is equal to anilinium ion. Yes, that compound is called anilinium ion. Now when you are coming to anilinium ion is meta-directing. Anilinium ion, there is no lone pair here. When anybody is losing lone pair, it will not show plus R effect. It will be meta-directing here. So this is meta-directing. So some amount of aniline undergo protonation to form anilinium ion, and because of that generation of anilinium ion, some amount of aniline is found to be meta-directing. So this is a reason why aniline, some amount of aniline, not every amount, almost 47% of aniline is converted into meta-nitroaniline upon direct nitration. So now coming back to the question. Okay, listen. Even though NH2 group is ortho-para-directing, in electrophilic substitution reactions, aniline upon direct nitration gives some amount of meta-nitroaniline. Assertion correct, no doubt. Assertion is correct. Reason: aniline in presence of acid, this is acid, form anilinium ion which is meta-directing. Reason is correct. So assertion correct, reason correct, correct explanation. This is an important concept. Any way they will ask, they may change this assertion, reason, and they may ask the same concept. Learn that concept, it is sure. Okay, so both assertion and reason are true. Reason is the correct explanation. Remember that. Okay, so I think all of you got it. So I'm moving to the next question. Okay, we are a bit late now, just moving to the next question. Okay, see students, next one. Yes, In cold condition, aniline is diazotized and treated with aniline again to give colored product. What's the structure of colored product? We studied azodite test, coupling reaction. We are going to explain that. Okay. In cold condition, what is cold condition? Yes, this is aniline. This is aniline. In cold condition means very low temperature. Very low temperature. Diazotize. Diazotization means we are treating it with NaNO2 and HCl. NaNO2 and HCl. Yes. At 273 Kelvin, very low temperature. You will get benzene diazonium chloride. We know that this is benzene diazonium chloride, N2Cl. No doubt. Aniline, upon diazotization, you will get benzene diazonium chloride. Diazotized means reaction with nitrous acid at a very low temperature. This compound is called benzene diazonium chloride. Now read the next sentence. Again, this benzene diazonium chloride reacts with aniline. Yes, this is benzene diazonium chloride. This is benzene diazonium chloride. N double bond N2Cl. I can say N2Cl, N2Cl, N2Cl. Yes, we are treating it with aniline. This is aniline. Yes, this is aniline. NH2, no doubt. Aniline. In presence of aniline is basic. This is done in presence of acidic medium. So what is happening? You know what will happen? Here, listen. So here we can say, here there is para position, there is hydrogen. There is hydrogen here. So they will react each other to produce, you know, azo dye, a colored dye, yellow colored dye. So what's the answer here? You will get a dye like that. This is equal to coupling reaction. We studied before. You will get a structure like that. Benzene ring with the N double bond N. Again benzene ring and with NH2. This is called colored compound. This colored compound is equal to, you know, para amino azobenzene. This has yellow color compound. We studied this reaction. We call it as coupling reaction. We are removing HCl from here and you are getting colored compound. Now see, which is the structure of colored compound they are asking. Remember, aniline upon diazotized to form some compound, and that compound again treating with aniline to form a colored compound. What's the structure of colored compound? Yes, structure of colored compound is like that. Benzene ring, N double bond N, benzene ring, NH2. This is the colored compound. This is equal to para amino azobenzene. The name of the compound is para amino azobenzene. We know that. Okay. And this compound, what is the structure of this colored compound they are asking? Yes, structure of the colored compound is found to be this is the structure, option B. Okay. It's very easy, direct question. So it is little, you have to write and check the answer, then only you will get it. So this is your answer. So this is para amino azobenzene. So option B is your answer. Okay. Now last one. You are doing the last question. I think all of you got it, right? Students, you got it or not? Yes or no? So we are moving to the next question. Okay. So I'm just giving an equation. We know that we are just completing the equation. Anybody can tell me the answer here? Anybody? I'm just giving 1 minute to you. Tell me the answer fast. Aniline, on treating it with NaNO2 and HCl, you will get A. CuCN, you will get B. LiAlH4, you will get C. What is C? They are asking what is C. Okay. Anybody can tell me the answer fast? Anybody? Waiting for your answer. Yes. So I'm doing here. This is aniline, right? Yes, I didn't get any answer. Tell me. Okay, we will discuss. Wait. Aniline, on treating it with NaNO2 and HCl. NaNO2 and HCl at 0 degrees Celsius, you will get benzene diazonium chloride. No doubt, this is benzene diazonium chloride, N2Cl, right? N2Cl, benzene diazonium chloride. Then, this benzene diazonium chloride, on treating it with the CuCN, you studied CuCN. Okay, CuCN and KCN must be there. They are not giving KCN, they must give KCN also. KCN in presence of CuCN. KCN in presence of CuCN. You can add KCN, no problem, it is given in the reader. You will get benzonitrile. You will get benzonitrile. This is benzene ring with the Cl. Benzonitrile. That is this B. Benzonitrile, on treating it with LiAlH4, what is our answer? We studied in the first part of this session. Cyanide or nitrile become primary amine. So you will get benzene ring with the CH2NH2. This is the final product obtained. You got the final product, but you should know the name also. What is the name of this compound? Anybody? Yes, this is equal to benzyl amine. The answer is benzyl amine. Okay, so remember, these are the topics. So just go through this chapter. It is an easy chapter. Don't miss the session. Don't miss the important points what we discuss here. Just go and study. Okay, so now I think all of you are okay up to this. Yes or no? Okay, now Ashwin sir will come after 2 minutes. Then he will continue with the coordination chemistry. Okay, okay then, bye.
Good afternoon. Hi all. Who is here in this live? Who is here? Humaid, Vasant is here. Yes, Nabil. Sean is here. Hi Sean. Alan. Anybody else? Who is here in this live? Yes. Okay. Okay, hope you guys are doing well. Okay, Akshay is here. Yes, and today we are going to discuss some questions from the topic coordination compounds, which is having 7 marks of weightage. Okay, and you know, today we will discuss some questions related to the topics like the terminologies of coordination compounds and IUPAC nomenclature of coordination compounds, and VBT is there, valence bond theory is there, and the CFT is there, crystal field splitting theory is there, and also isomerism. Okay, so let's start. We can move on to the first question. So what is the first question? Which of the following ligands form a chelate complex with a metal ion? Okay, that is the question. Which of the following ligands form chelate complex with metal ion? So what do you mean by chelate? What do you mean by chelate ligand? You know that chelate ligand is bidentate or polydentate ligand. So what do you mean by bidentate or polydentate? You have to know that, right? So bidentate means bidentate means you can see, for example, I'm taking ethane 1,2 diamine. Okay, I'm taking ethane 1,2 diamine, ethane 1,2 diamine. Okay, ethane 1,2 diamine. So you know what is the structure of ethane 1,2 diamine? It will be NH2, CH2, CH2 and NH2, right? NH2, CH2, CH2 and NH2. And you know what is central metal? You can see that this, from this ligand, that is ethane 1,2 diamine is the ligand here, and from this ligand 2 donor atoms will be there. What do you mean by donor atoms? What do you mean by donor atoms? Donor atoms are atoms of ligands which will directly bond with central metal. Okay, so here in this ethane 1,2 diamine ligand, you can see that there are 2 donor atoms, right? There are 2 donor atoms. So ligands having 2 donor atoms are known as bidentate ligand. They are known as bidentate ligand. Bidentate ligand. Okay, bidentate ligand. You know, if it have 3 donor atom, then we can call it as tridentate ligand. If it is 4, it will be tetradentate. And can you please give me an example for a hexadentate ligand? Anyone? Ashwini is there, Hadiya is there, then Vishnu Shankar is there, Alan, Humayt. Anyone? Can you please give me an example for hexadentate ligand? Anyone? Hexadentate ligand. Yes, EDTA is there. Vasant, very good. EDTA, very good. EDTA, ethylene diamine tetraacetate, which is a hexadentate ligand. Hexadentate means there will be 6 donor atoms, right? So in general, we can call it like, if there are 2 donor atoms, they are bidentate ligand, and if there is more than 2 donor atoms, then you can generally call it as polydentate ligand. So coming to the point, what is chelate? Chelate ligand means they will be bidentate or polydentate ligand which can form a ring with the central metal. Okay, say for example, here you can see ethane 1,2 diamine. This is ethane 1,2 diamine, right? They are bidentate ligand. You can see there will be 2 donor atoms, right? So they are bidentate ligand, and you can see this ligand can form a ring with the central metal, right? This is a ring. This is closed, right? Starting from the central metal and closing with the central metal. So they can form a ring, right? So ring forming ligands are known as chelate. And here in this option you can see H2O. You know H2O is monodentate. What do you mean by mono? Mono or uni means mono or unidentate means only 1 donor atom will be there. So H2O is monodentate or unidentate, CN is also a unidentate or monodentate ligand, and Cl is also a monodentate and a unidentate ligand. So C2O4 minus. What is C2O4 minus? It is oxalate ion, and you know oxalate is bidentate. Oxalate is bidentate. Okay, so oxalate is bidentate. You know the structure of oxalate? You know the structure of oxalate? This will be the structure of oxalate, like COO minus and COO minus. So when they form, you know, when this oxalate form bond with the central metal, it will be like this: C double bond O, C double bond O, and they will form a ring. You can see here they will form a ring. You can see a ring here. Yes, you can see a ring here. So this is C2O4 minus. C2O4 minus. That is your the ligand's name is oxalate ion. Oxalate ion. Okay, oxalate ion. So since oxalate ion is bidentate, they can form a ring. So which is the chelate here? Which is the chelate here? C2O4 minus. That is oxalate ion will be the chelate here. That's it. Simple question. It's a simple question from the terminology of coordination compound. You have to know the term. What is bidentate? What is polydentate? What is unidentate? And you have to know the term chelate also. Okay, that's it. Okay, and moving on to the second question, which is coordination number of cobalt in the complex COEN thrice 3 plus. This is also simple. This is also a question from the terminology. Okay, so first of all, if you are studying coordination compounds, you have to know the terminologies, because coordination compound is a new chapter or new subject or new topic for your 12th standard, right? So you have to know the terminology. So coordination number, what is coordination number? And I'm taking the coordination compound here, it will be cobalt. Cobalt. How many En is there? What is En? It is ethane 1, 2 diamine. So you know cobalt has a coordination like En, right? En. This is ethane 1, 2 diamine. As I told you, you know that ethane 1, 2 diamine is a bidentate ligand. So that you can write it like this. How will be the En? How will be the ethane 1, 2 diamine? You can see here. This will be 1 En like this. This will be 1 En, ethane 1, 2 diamine. And this will be another En, ethane 1, 2 diamine. And this will be another En. This will be ethane 1, 2 diamine. Okay. And why I am drawing like it? You can see that since ethane 1, 2 diamine is a bidentate ligand, there will be 2 donor atoms, right? 1, 2. There will be 2 donor atoms will be there. Here also there will be 2 donor atoms. And here also there will be 2 donor atoms will be there. Okay. So how many donor atoms total? How many donor atoms are there? 1, 2, 3, 4, 5, 6. Okay. So total 6 donor atoms are there, right? Yes. The number of donor atoms are known as coordination number. Okay. So what is the question here? What is the question here? Coordination number of cobalt in this complex. So what is the coordination number? Now you know the coordination number, right? So what is coordination number? It is the number of donor atoms. Okay. Donor atom means atom of ligand which is directly attached to the central metal. So how many donor atoms are there? 6 donor atoms are there. So coordination number will be 6. That's it. Simple. Okay. So this is also a question from the terminology part of coordination compounds. Okay, understood? Understood? Yes, Yuva is here. Hi Yuva. Hamesh is there. Yes. Yes, next question is an assertion reason question. You can see the assertion. What is assertion here? Platinum En twice. Again that En came. That is En is ethane 1, 2 diamine. Yes. You know that is bidentate, right? Yes, okay. Then what is assertion? Platinum En twice Cl2 2 plus complex is less stable than platinum NH3 4 times Cl2 2 plus complex. What do you think? Is that assertion right? What do you think, Yuva? Is that assertion right? What do you think? Yes, sterilence, right? Sterilence, yes. He's saying that, yes, KBFC win. Yes, Kerala Blasters win. I'm also a Kerala Blasters fan. Okay, KBFC wins. Yes, good. That is not the subject here. You can see assertion. In assertion, platinum En twice Cl2 2 plus complex is less stable than platinum NH3 4 times Cl2 2 plus. That is, you can see that the first compound is platinum En twice Cl2 2 plus. Okay. Okay, so we can draw the structure. I'm drawing the structure like this: platinum, En twice. So there will be 2 En, right? This will be 1 En and this will be another En. Okay, and Cl2, there will be 2 chlorine also. Okay, and here what is the next compound? Platinum, NH3 4 times, and Cl2 2 plus, right? Cl2 2 plus. Okay, so what is here? You can see that platinum, then NH3 4 times, NH3 4 times, and Cl2. Okay, Cl2. Okay, so here you can see that there are no chelating ligands for this compound. Can you see any chelating ligand? Not at all, right? But in the first compound you can see there are 2 chelating ligands, right? Chelating ligands. And you know the chelating effect? If there are chelating ligands, they will be more stable. Thermodynamically, they will be more stable. Okay, so the first compound should be more stable than the second compound, because first compound is having chelating ligand. Okay, but in second compound you can't see any chelating ligand. You know the chelating ligand, right? That we have already studied from the first question itself. Okay, so you can see the assertion should be like this, like the first compound is more stable than the second compound, but assertion here is it is less stable. So assertion itself, it's a wrong, it's incorrect. So assertion is incorrect, because according to chelating effect, the compound having chelating ligand should be more stable than compounds having non-chelating ligand. Okay, so assertion is wrong. So what about reason? You can see that platinum En twice Cl2 2 plus complex shows chelating effect. That is, we have already discussed, right? We have already discussed it. That is, this compound has chelating ligand, so they will have chelating effect. So reason is correct. Assertion is incorrect, and reason is correct. That's it. Okay, understood? Everything is fine, right? Everything is fine. Yes. Okay. Anyway, we can move on to the next question. This is a question from the concept, Werner's theory. You know what is Werner's theory? Yes. What is Werner's theory? Werner's theory mainly suggesting that in a coordination compound there will be 2 types of linkages. That is primary linkage and secondary linkage, or you can call it as primary valency or secondary valency. Okay, so this is a question in which you have to apply the Werner's theory. So we can move on to the question. 1 mole of CrCl3.6H2O compound reacts with excess AgNO3 solution to yield 2 moles of AgCl. The structural formula of the compound is, that is the structure. The question is like, what is the formula of the compound? And the hint is, a compound is, a formula is given actually, CrCl3.6H2O. This is the formula. Okay, it is given. And it is reacting with excess AgNO3. It is reacting with excess AgNO3. It is reacting with excess AgNO3. And 2 moles of AgCl is formed. 2 moles of AgCl is formed. This is what is given in this question, right? And how can we find the molecular formula or the structural formula of the compound? How can we find the structural formula? Yes. For finding the structural formula, you have to know what is oxidation or what is primary linkage or primary valency. Here you can see that how many AgCl is formed? 2 moles of AgCl is formed, right? 2 moles of AgCl is formed. You know that from 1 AgCl, 1 Ag plus and 1 Cl minus will be formed, right? So from 2 moles of AgCl, 2 Ag plus and 2 Cl minus will be formed. Is that clear? Yes. Because in the question it is clear that 2 moles of AgCl is formed. So when 2 moles of AgCl is formed, 2 moles of Cl minus will be there. It is indicating that from here it is very much clear that in the structural formula of the coordination compound there will be 2 chlorine atoms outside the coordination sphere. The square bracket is known as coordination sphere, right? So out of the coordination sphere or outside the coordination sphere, you can see that there will be 2 chlorine atoms. How I got 2 chlorine here? There is a hint in the question that 2 moles of AgCl is formed. If 2 moles of AgCl is formed, 2 moles of Cl minus will be there. If 2 moles of Cl minus is there, then 2 chlorine atom will be there in the outside of the coordination sphere. Then what is left in this equation? How many chlorine is left? Only 1 chlorine is left. I'm putting like here. 1 chlorine will be there. Okay, then what is remaining? Cr is the central metal. And how many H2O is here? 6 H2O are there. 6 H2O are there. But you know that chromium, this is chromium, right? Central metal is chromium. Chromium has a coordination number of 6. Generally, they will have a coordination number of 6, right? So, you know that there will be already 1 chlorine is attached to chromium, right? So 5 bonds are remaining. So to that 5 bond, there will be 5 H2O. You can write it like this, 5 H2O. Okay. So the compound will be like Cr H2O 5 times Cl and Cl2 in the outside, and 1 more H2O is there, right? 1 more H2O is remaining. You can put it like hydrate H2O. That's it. So from the given hint, we got the structural formula of the coordination compound. Simple. So what is the hint here? This is actually an application of Werner's theory. You know the primary valency, it is indicated by the oxidation number, it is ionizable, right? And this chlorine is ionizable. Okay, this chlorine, you know, when this coordination compound, when it undergo ionization, it will ionize like this, you know, the chlorine outside the sphere, they will ionize like 2Cl minus, and this sphere will be like 2 plus. Okay, so this ionizing valency is known as primary valency. So here you can see that from the hint that is given in this question, 2 moles of AgCl is formed, so 2 chlorine minus is formed, so 2 chlorine will be outside in the coordination sphere, then the rest is written inside the coordination sphere. That's it, simple. Okay, so the answer will be, which is the answer? Cr H2O 5 times Cl, Cl2 dot H2O. Cr H2O 5 times Cl, Cl2 dot H2O. Yeah, option A is the correct answer. Option A will be the correct answer. Okay, option A will be the correct answer. That's it. Okay, then we can move on to the next question. Write the IUPAC name. Yes, we are going to do the IUPAC name of coordination compounds. Yes, a coordination compound is given, which is very simple. Okay, how can we write the coordination, the IUPAC name of this coordination compound? How can we write it? You can see that, always listen, always if you are going to write the IUPAC name of a coordination compound, you can split the coordination compounds into 2. Like, you know, the coordination compounds will be like this. Either it will be like this, a sphere into counter ion. Yeah, and counter ion or sphere. Or there will be 2 spheres. Coordination spheres will be there. Like that. Okay, so these kind of, or it will be like this. The coordination compound, you can expect like this. And you can expect also like this. Okay, so you know, the coordination compounds may be like this, of this type. But here you can see that you can consider this coordination compound into 2 parts. This will be positive part and this will be negative part. Okay, here also this is first part, second part, first part, second part. This is only having one part. And you know the first part will be always positive, or you can call it as cationic part. The first part will be always positive. Here this is the first part and here this is the first part. So first part will be always positive. Just like the ionic compounds like NaCl, you know NaCl in the first part is Na plus, right? And second part is Cl minus, like that. Okay, like that the first part will be positive and second part will be negative. So always start with first part, that is positive part. What is here in positive part? It is a sphere, right? You can see this is a sphere and a counter ion, just like this, just like this. Okay, just like this type. Okay, so we can start naming it. For naming this compound, first of all you have to name its ligands. So what are its ligands here? You can see what are its ligands. Chlorine is there, NH3 is there, right? What is the name of chlorine? When it came as ligand, you can call it as chlorido. Okay, so this will be chlorido. And NH3, for NH3 we can write it like amino. Okay, we can write it like amino group. And NH2 amine group, you can call it as amine group. For NH3 it is amine. And NH2CH3, what is NH2CH3? It is methylamine. So the chlorido, methylamine and amine group. Okay, amine group. What do you think? If there are more than one ligand, you can follow the alphabetical order. So according to alphabetical order, you have to name the amine first, right? Because amine is starting with A, so you can start with, like, there are two amines, right? Two NH3 is there, so you can name it like diamine. Then what is next? A, after A it is C, right? So diamine, one chlorine is there, right? So you can write it as one chlorido, diamine, chlorido or chloro, both are same. Okay, so you can write chlorido or chloro. So chlorido. Then what is left here? This ligand. What is this ligand? Methylamine. So you can write it like methylamine. Okay, so diamine, chlorido, methylamine, and what is here in the central metal? After writing the name of ligand, you have to write the name of central metal. What is central metal here? It is platinum, right? So I'm writing platinum. I'm writing it as platinum. Okay, then you have to put the oxidation number of platinum in brackets. So what is the oxidation number here? How can we find oxidation number? Here listen, how can we find oxidation number? For finding oxidation number, start with counter ion. What is counter ion here? It is chlorine. What is the charge of chlorine? It is -1, right? It is -1. So if the negative part is -1, positive part should be +1. The positive part should be +1. Just like the Na plus and Cl minus. Okay, if the negative part is -1, positive part should be +1. So I'm writing it as plus. Okay, plus. So this has a plus charge, and you have to find the oxidation state of platinum. I'm taking it as X, and chlorine it will be -1, and methylamine the charge is 0, and NH3 the charge is 0. That you know the charge of ligands, right? So you can find what is here, X plus charge of oxidation state of platinum is X. Then what is the oxidation state of chlorine? It is -1, plus what is the charge of methylamine? It is 0. And what is the charge of NH3? It is also 0. And total you will get a plus charge, right? +1 charge. You will get plus charge means +1 charge. So X will be equal to 1, and you can take this -1 into the right side. It will be 1 plus 1, that is +2. So the oxidation state of platinum here is +2. So I am writing it like 2. So we finish the first part. The first part is sphere part. You can see there is a ligands like NH3, methylamine and chlorine. We done the naming of ligands, and after that we done the naming of central metal also. Okay, then what is remaining here? There is a chlorine, right? So you can write it like chloride. You can write it like chloride. If there is chlorine as counter ion, you can write it like chloride. So the name is diamine chlorido methylamine platinum 2 chloride. That's it. Okay, so this is the IUPAC nomenclature of, yes, very good. Vasant is there, and Hadia is there. Okay. Yes. Diamine chlorido methylamine platinum 2 chloride. That is the correct answer. Okay, then we can move on to the next question, which is also an IUPAC nomenclature, and you know we can't skip this question because it is it's a very good question and it's difficult too, because you can see that the given coordination compound is, it has two spheres, that is two coordination spheres are there, right? Two coordination spheres are there. So what is here, you can see that, yes, we can do it. Listen here. The compound is CO, that is cobalt, En thrice, twice. Okay, and here what is here? Fe, Cn 6 times, thrice. Okay, you can see there is 2 and 3 for the coordination spheres. So how can we do the naming of this compound? This is very, you may feel very difficult, but it is simple. How can we do this? How can we do this? You can do like this. You know, you can also consider the concept of positive part and negative part. Okay, that is cationic part and anionic part. Okay, and you know, from the equation, from the chemical equation, you can see that, say for example, Al2O3. Okay, you can see the valency of aluminium. The valency of aluminium is there below the oxygen, and valency of oxygen is there below the aluminium. Just like that, the charge, yes, aluminium is in +3 charge, oxygen is in -2 charge, right? So valency of oxygen is there below the aluminium, and valency of aluminium is there below the oxygen, right? So just like that, what is the valency of this compound, or what is the charge of this compound? What will be the charge of this compound? What do you think? This will be the charge, right? Since it is a positive part or cationic part, it will be +3. Okay, just compare with this. Okay, if you feel difficult, compare with this compound. And here also, you know, what will be the charge of this compound? It will be like this, right? 2. It will be 2. And you know, since it is negative part or anionic part, the charge will be -2. So you can see that for cobalt, En thrice, the charge will be +3. Okay, and Fe, Cn 6 times, charge will be -2. That's it. And if you have any doubts, or if you can check it whether you are right or wrong. You can check it. How can we check it? You can check the total charge. What is the total charge of positive part? +3. For 1 square it is +3. How many square is there? 2 squares are there. 2 coordination spheres are there, right? So +3 into 2, it will be +6. And what is the charge here? For 1 sphere it is -2. So how many spheres are there? 3 spheres are there. So for total 3 spheres, total charge will be -6. So now it is clear. +6 and -6, it will be 0. So you are right. We are doing good. Okay. So how can we find this coordination number? Oxidation number of cobalt and iron? You can find it like, yes, I'm taking oxidation number of cobalt as X, and I'm taking ethane 1,2, charge of ethane 1,2 as 0. Okay, so what will be the oxidation state of cobalt? Yes, the oxidation state or oxidation number of cobalt will be equal to, yes, X, then plus 0, it is equal to, yes, X plus 0 equal to +3, right? X plus 0, X plus 0 into 3. 0 into 3 will be equal to +3. So X will be equal to +3. So the oxidation state of cobalt is +3. So we got oxidation state of cobalt. Okay. Then what is the oxidation state of iron here? You can put it like the oxidation state of iron as X, and you know the charge of Cn is -1. So what will be the oxidation state here? You know, X for iron it is X plus. For 1 Cn it is -1. How many Cn is here? 6 Cn. So -1 into 6, it will be equal to -2. So X minus 6 will be equal to -2, and X equal to -2 plus 6, that is +4. +4. So we got the oxidation state of both cobalt and iron. That will be the most difficult part of this question. Okay, that's why I done it first. Okay, otherwise you can do the nomenclature. You know the nomenclature, right? So now you can easily do the nomenclature. Try it. Okay, try it. Lakshmi is there. Yes. Vasant. It will be tris ethane 1,2 diamine cobalt 3 hexacyanoferrate 4. Very good, Vasant. Yes. Hero. Who is that hero? Yes, hero, you are right. You are a hero. Okay, but hero, one mistake is there. In ferrate it is oxidation number is 4, right? Why you put 3 here? Okay, now it is clear. You can see it is 4. So what will be the name? We can write the name. Starting with the positive part. What is the positive part here? This is the positive part. Okay, starting with the ligand. What is ligand? Ethane 1,2 diamine, right? How many ethane 1,2 diamine is there? 3, right? So you can write it like tris ethane 1,2 diamine, tris ethane 1,2 diamine. Then what is here? I mean, we finish the naming of ligand, and what is left? Central metal. What is central metal? Cobalt. Yes. And what is the oxidation state of cobalt? 3, right? So you can write like 3. So we finish the positive part. Then we can move on to the negative part. What is negative part? Negative part is also a sphere, right? So you can start it with the nomenclature of ligand. How many Cn is there? 6 Cn is there. So you can write it like hexacyano. Cn is cyano group, right? So you can write it like hexacyano. Then what is here? Iron. Fe is actually iron, right? But you know, if the central metal is the negative part, you have to write the name of central metal with the ate. You have to add ate. So it will not be like ionate, it will be like ferrate. Okay, ferrate, because you have to use the Latin name, right? You have to use the Latin name. So what is the Latin name of iron? It is ferrum, right? So you can add it like ferrate. Then what is the oxidation state? +4. So that's it. So this is actually the nomenclature of this compound. Okay, understood? Is there any doubt? Tris En cobalt 3 hexacyanoferrate 4. Yes, Hadia, that's right. Okay, yes. And now we can move on to the next question. The formula of the coordination compound. IUPAC nomenclature is given, then you can find the formula. I think it is very easy. We can make it fast. Okay, that is tetraamine. Amine means NH3, right? NH3. Tetra means it will be 4. So 4 times. Then chlorido means there will be chlorine as ligand. And nitrito N. You know, nitrito group may be NO2 or ONO. Both are NO2 group, nitrito group. But in the question it is clear that it is nitrito N. What do you mean by nitrito N? What is the difference between nitrito N and nitrito O? This will be nitrito N and this will be nitrito O. What is this N and O indicating? You know, the N indicating N is, in this case, N is making the bond with the central metal. Okay, N is making the bond with the central metal. And here you can see nitrito O. That means oxygen is making bond with the central metal. Okay, is that clear? Is that clear? That's it. Okay, so now it is clear that here it is nitrito N. So you can write it like NO2, not ONO. It is nitrito N. So you nitrito N, it will be NO2, not ONO. NO2. I'm writing it as NO2. And what is here as central metal? Cobalt. Cobalt. So this will be the compound. And you have to put the chloride, right? How can we put the chloride? How can we know the number? Since it is chloride, this will be here, it will be chlorine. But how many chlorine will be there? Is it 1, 2 or 3? How can we know that? For finding that how many chlorine will be there, you can use this method. That is, what is the oxidation state of cobalt? It is +3. What is the charge of chlorine? It is -1. You know that. And what is the charge of NH3? It is 0. What is the charge of NO2? It is -1. So what will be the total charge of positive part? What will be the total charge? Total charge +3, -1 and -1. It will be +1, right? So the positive part has +1 charge. So the negative part will also has, it will have -1 charge. Because both positive and negative part should be equal and opposite. So here you can see that the positive part is +1. So the negative part should be -1. And you know that for 1 chlorine charge is -1. So it is okay. For 1 chlorine it is already -1. So the negative part has already -1 charge. So it is balanced. So this will be the answer. Okay, this will be the answer. So this is the IUPAC nomenclature of compound. Yes. Okay. So what will be the charge? It will be like, the option will be, yeah, what is the option? What is the option? CO NH3 4 times Cl NO2 Cl. This option C will be the answer. You can write Cl or NO2 first or second, that's no matter here. So option C will be the answer. Okay, option C will be the answer. Okay, that's it. Then we can move on to the next question. Write the IUPAC name of ionization isomer of NiNH3 thrice NO3Cl. So a compound is given. Actually, this is a question. It's a combined question from IUPAC nomenclature and isomerism. You have to know what is ionization isomerism. So what is ionization isomerism? You can see NiNH3 thrice NO3 chlorine. This is the compound, right? This is the compound. And what will be its ionization isomer? What do you mean by ionization isomer? You know, ionization isomerism means the counterion itself can act as a potential ligand. So there will be some interchange of, or there will be some exchange of ions outside and inside the sphere. Okay, that is, you know that chlorine has -1 charge and NO3 is also having -1 charge. So if you want to write the ionization isomer, just exchange them like this: nickel NH3 thrice, and instead of NO3 you can write chlorine, and NO3 will be like counterion. Okay, and NO3 will become counterion. And now you can see this is ionization isomerism. You can see that there are, the molecular formula will be same: 1 Ni, 1 Ni, 3 NH3, 3 NH3, 1 chlorine, 1 chlorine, and 1 NO3, 1 NO3. So the molecular formula is same, but it is the counterion. But it is the ionization isomer, because you can see that here in the first case chlorine was counter ion, but here chlorine is as ligand. Chlorine is ligand. You can see that chlorine is ligand. And here in the first case NO3 was ligand, and in the second case now NO3 is counter ion, like that. Okay, then you can name it. Okay, I'm not wasting the time because we have already done some nomenclature, so you can name it. Okay, that's for you guys. Okay, you can name it. Okay, many of you already named it. Okay, yes, we can move on to the next question. Next question, which of the following ions can exhibit optical isomerism? I know most of the students will have some difficulty in studying the geometrical isomerism and optical isomerism part from this chapter. Okay, from this chapter they feel very difficult for finding the optical isomers or geometrical isomers. So now we are going to discuss a simple trick for finding optical isomerism. Okay, you can also try it. So how can we find this compound will undergo, whether this compound will show optical isomerism or not? How can we identify that? There are several methods. You can use the mirror image method. If the mirror image, you can take the mirror image, and if it is non-superimposable, yes, that method is okay. You can use that. But here I am going to use some different method. Okay, so how it will be? Option A, I'm taking option A. Option A, you can see that cobalt and NH3 4 times Cl2, right? So it is having 4 bonds, and NH3 4 times, there will be 4 NH3. I'm writing like NH3 and NH3. So I'm writing 4 NH3 groups, and 2 chlorine is there, right? So I'm writing 2 chlorine is there. Okay, and you can see there will be a plus charge. So this is the option A compound, right? Yes. Then how can we identify, or how can we find which is having optical isomerism? You can use plane of symmetry concept. What do you mean by plane of symmetry? You know what is plane of symmetry? If an imaginary line passes through a molecule, okay, if an imaginary line is passing through the molecule, if you got 2 equal halves, then that is what is known as plane of symmetry. That plane is known as plane of symmetry. But if you don't know plane of symmetry, leave it. You can try this. Only remember this trick. Okay, if it is having plane of symmetry, it will be optically inactive. Okay, or if it is not having plane of symmetry, it will be optically active. Only remember this point. Okay, if a compound is having plane of symmetry, if you don't know plane of symmetry, you just leave the the definition or concept behind plane of symmetry. Just remember this point, POS, that is plane of symmetry. If it has plane of symmetry, it will be optically inactive. If it does not have any plane of symmetry, it will be optically active. And the doubt came, that is, sir, how can we find plane of symmetry? And how can we know which is having plane of symmetry? That's the doubt, right? I will solve it. Okay, you can use this trick, that is, in a coordination compound, okay, in a coordination compound, if there are equal groups, the same groups are in opposite side. Okay, same groups, that is same, if same ligands are in opposite, you can see ligand and ligand, same ligands are in opposite, right? So it has plane of symmetry. If equal ligands are there in opposite, it has plane of symmetry. If it has plane of symmetry, it will be optically inactive. Okay, it will be optically inactive. And the next method is like this. Maybe the opposite. Here it is ligand and here it is X. Okay, the sidewise ligand, if the sidewise ligand are same, okay, if the ligand in the side is same, then also it has plane of symmetry. Then now also it has plane of symmetry. So it will be optically inactive. It will be optically inactive. This is another method. So there are two conditions for a compound having the plane of symmetry. That is, if there are two equal groups are in opposite side, it will have plane of symmetry and the compound will be optically inactive. Okay, and if the opposite groups are different and the sideways groups are same, if the sideways groups are same, then it also will have plane of symmetry. Okay, then it will be optically inactive. Then what is the condition for optically active case? That is, it is like this. Listen, it will be like this. A compound is here and it is not having same ligand. It is not having same ligand. Okay, it is not having same ligand. And in opposite wise or in sidewise also, it is not having any same ligand. All are different. Okay, this is different and here also it is different. So it has no plane of symmetry. It has no plane of symmetry. It has no plane of symmetry. So this will be optically active. This will be optically active. Please note this. Okay, please note this point and this also. It will be very easy. You can predict any compound. You can predict the optical isomers of any compound. You don't have to by heart any kind of type of coordination compounds or like that. You don't have to by heart it. Okay, you can find the optical isomerism or optical isomers of any coordination compound using this method. Okay. Okay, you note it? Then check the optical isomerism of this compound. What will be the optical isomerism of this compound? You can see there is same groups in opposite side, right? Same groups in opposite side. Same groups in opposite side. So this will be having plane of symmetry. This will be having plane of symmetry. So this will be optically inactive. This will be optically inactive. This will be optically inactive. Okay, so the first point is optically inactive. It will not form any optical isomers. Okay, what about the second thing? What about the second thing? You can draw the second. You can draw the second one. Yes, I'm doing the second one. It will be cobalt NH32. I'm writing it NH32 Cl4. Here also you can see that there are same groups, same ligands are in opposite, right? Same ligands are there in opposite. If same ligands are in opposite side, it will have plane of symmetry. If it has plane of symmetry, it will be optically inactive. It will be optically inactive. That's it. So this is also optically inactive. It will not form any optical isomerism. Okay. And what about the third one? Third one. It will be cis. Cobalt En twice Cl2. I'm writing cobalt. And cobalt is having coordination number 6. And since it is cis, you know the cis, right? Cis geometrical isomer is indicating same ligands will be in same side. And En twice, so 2 En groups are there. So this is 2 En groups. 2 En groups will be there like this. 2 En groups. Okay, 2 En groups. And here you can see that there are no ligands, no same ligands in opposite side. No same ligands. This is chlorine and this is En. Okay, so no same ligands are there in opposite side. And here also you can see that no same ligands in opposite side. So it is not having plane of symmetry. It is not having plane of symmetry. So this will be optically active. So they will form optical isomers. The correct answer is option C. The correct answer is option C. That's it. Okay, you understood the point. That is very simple, you know. It is very simple. If you use this concept, this trick, it will be very easy. Even for the competitive exams, you can use this method. Okay. That's it. Moving on to the next question, that is for the complex. A complex is given FeEn twice Cl2Cl. Identify the following that is oxidation number. You have, first of all, you have to know what is the oxidation number of iron. Here, this iron. Find the oxidation number, and hybrid orbitals, that is hybridization. You have to find the hybridization, and shape, that is geometry or arrangement, and the magnetic behavior itself. You have to find it. So how can we draw this? You know, Fe, and this will be En twice. En twice. I'm writing like En twice. So I'm writing yes, Fe, En twice, Cl2 and Cl. Okay, what is the first question? What is the first question? You have to find the oxidation number of iron. Find it, find it. What will be the oxidation state? You can send me the message. Okay, message me. +3. Yes, +3. Let me check. Okay, yes. For chlorine, it will be -1, right? So the negative part will be -1. So what will be the positive part? It will be +1, right? So you can write it like +1. +1. So I'm writing the oxidation state of iron as X, and En will be 0 and chlorine will be -1. Okay, so how can we find the oxidation state? X plus 0, this is 0, plus what is the oxidation state of chlorine? -1 into 2 will be equal to, what is the charge? +1. So X minus 2 equal to +1, so X will be equal to +3. Very good, very good. Some of you already sent it. Okay, send it. Hadia is there, hero, again hero. Vasant is there, +3. Very good. So you got oxidation state of iron as +3. And what is the hybridization? How can we find hybridization? Using this oxidation state, now you know iron is in +3 oxidation state. Iron is in +3 oxidation state. That will be, that is oxidation state of iron. I mean, the iron will be Fe3+. Then you can write the electronic configuration of Fe3+. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d6. This will be the electronic configuration of iron, right? This is the electronic configuration of iron. But here you can see it is not iron, it is not just Fe, it is Fe3+. 3+ means 3 electrons will be donated. So 2 from 4s and 1 from 3d. So now how many electrons are there in 3d? 5 electrons are there in 3d. So I'm writing like orbital. I'm drawing the orbital diagram. Always draw the orbital diagram. I'm writing like orbital diagram like here. 3d, it will be 3d. This is 3d. Okay, and 4s will be there and 4p will be here. Okay, 4p. So how many electrons are there in 3d? You can see 1, 2, 3, 4, 5. 5 electrons are there in 3d, right? And the question or the doubt of student will be like this. Sir, it is having 2 ligands. One is strong and another is weak. En is a strong ligand and chlorine is a weak ligand. So, sir, I mean, is pairing will take place here? Will pairing take place here? What do you think? Yes. If there are 2 ligands, if one is strong and one is weak, you can take the strong ligand, the effect of strong ligand. If there any strong ligand, pairing will take place. Don't worry about the weak ligand. Okay, don't worry about the weak ligand. If there are any strong ligands, pairing will take place. So you can see in this compound there is strong ligand. So pairing will take place. So since En is a strong ligand, En is a strong ligand, pairing will take place. Okay, pairing will take place. Pairing will take place. Pairing will take place. So how it get paired? You can see this. Okay, so the the orbital diagram will be like this. Now it will be like this. 1, 2, 3, 4, 5. So you can see that after pairing, the diagram will be like this. 3D diagram will be like this. The orbital diagram of 3D will be like this. And orbital diagram of 4s will be like this. And 4p will be free. And you can see that since it has a coordination number 6, it need 6 empty orbitals. That is En twice. You know that En is bidendate. So for 1 En there will be 2 donor atoms. So for 2 En there will be 4 donor atoms. Total there will be 4 donor atoms from 2 En. And 2 chlorine there will be 2 donor atoms. So total how many donor atoms will be there? 6 donor atoms will be there. Okay, so you need 6 empty orbital. This is the concept of VBT. This is the concept of VBT. If you have 6 donor atoms, you need 6 empty orbitals from the central metal. So I'm taking empty orbital. This is not empty. Even though it is not paired, it is unpaired, right? It is unpaired, but you can't take it. You have to take the empty orbitals. Okay, so I'm taking empty orbitals, 2 empty orbitals from 3D. Taking 2 empty orbitals from 3D and 1 from 4s. Okay, so how many empty orbitals is here? 3, and 3 more we need. So I'm taking 3 p orbitals also. So now it is clear that what will be the hybrid orbitals here? 2d, 1s and 3p. It will be, the hybridization will be d2, d2sp3, d2sp3. That's it. So we got the hybridization of this compound. It will be d2sp3. The hybridization of this compound will be d2sp3. Is that okay? Hybridization will be d2sp3. Okay. Then you have to find the magnetic behavior. How can we find magnetic behavior? It is very easy. You know, how can we find magnetic behavior? It is very easy. You can find magnetic behavior like if there any unpaired electron, you can see this is the final orbital diagram, right? After pairing, this is the diagram. So you can see there is one unpaired electron. If there any unpaired electron, it will be paramagnetic. It will be paramagnetic. So now it is clear. We finish all the thing. You can see the first thing, oxidation state. This is oxidation state. Second thing, hybridization. D2sp3 is the hybridization. And the third thing, magnetic behavior. It is paramagnetic nature since it is having unpaired electrons. Is that clear? Understood? Yes. Very good. Okay. Very good. Very good. Yes. This is a good question. This is a very good question. You know, color of the coordination compounds depends on crystal field splitting. What will be the correct order of absorption of wavelength of light in the visible region? You have to, you have to write the correct order of absorption of wavelength of light. This is very important. This can be expected for your board exam. Okay. So how can we relate the splitting energy CFT with the color or the absorption of light? How can we relate it? Remember this point. Okay, remember this point. That is, if the ligand is having more splitting energy, that is, if the stronger the ligand, if more the splitting energy, stronger will be the ligand, right? So if the ligand is strong, what will happen? You know the equation, right? Planck's quantum theory. I mean, the change in energy will be, it will be equal to h nu. Nu can be written as C by lambda. It is there in the 11th standard structure of atom. And delta E will be hc by lambda. hc by lambda. And from this equation, it is very much clear that delta E and lambda are inversely proportional. Okay, this is Planck's quantum theory that you know, right? Yes. And delta E, that is if the change in energy, you can see that in splitting energy, the degenerate orbital, they will split like T2G and EG, right? T2G and EG. This is splitting energy, delta O, or you can write it like CFSE, splitting energy, crystal field splitting energy. If splitting energy is more, that is delta is more, you know the relation between energy change and lambda. If energy change increases, lambda will decrease because they are inversely proportional. So how can we relate all this? Remember, if CFSE, that is crystal field splitting energy or crystal field stabilizing energy, if it is greater, stronger will be the ligand. Okay, so the light they absorbed will be very weak, so lambda will be very low. Okay, so consider these compounds. in first compound you can see NH3 is the ligand. In the second compound you can see CN is the ligand, and in third you can see H2O is the ligand. Which is having more energy, which is more strong? You know the spectrochemical series, right? Spectrochemical series arrange the ligands in the based on the splitting energy. So you can see in spectrochemical series CN is having more, strong ligand. CN is much more strong ligand, and then NH3, then it is H2O. So which is stronger here? According to spectrochemical series, CN is the stronger ligand. So the wavelength absorbed by them, if the stronger the ligand, wavelength absorbed by them will be very weaker. So you can arrange it. Now you can arrange it in just opposite manner. You can arrange this in just opposite manner. Then you will get the order of wavelength. Because stronger the ligand, wavelength will be weaker or lesser. So we can write it like H2O is weak, right? So CO H2O 6 times 3 plus. Okay, and it is having more wavelength. Then it will be CONH3 6 times 3 plus and COCN 6 times 3 minus. Okay, so using the method you can easily identify the order of wavelength they absorbed, because you can see that CN is having CN is the strongest ligand. CN is strong ligand. Okay, so stronger the ligand, weaker will be the wavelength. So in the order of CFSEs it is stronger, but in the order of wavelength it will be in the last. Okay, so option C will be the answer. Understood? Understood? Yes. Okay. And now we can move on to the last question. Last question in the live. Last question. Assertion. It's an assertion reason question. Low spin octahedral complexes of nickel 2 plus ions are not known. Reason: inner 2 empty orbitals are not available. So the question, assertion, we can move on to the assertion. What is assertion? Low spin octahedral complex. It is low spin and it is octahedral also. It is low spin and it is octahedral also. So low spin octahedral complex of nickel 2 plus are not known. So how can we do this? How can we do this? Low spin. How can we do this? Low spin octahedral complex. What do you mean by low spin? What do you mean by low spin? Low spin means we will use inner d orbital. It can also call it as inner d complex, inner d orbital complexes. Okay. So octahedral means it will have octahedral structure. So we can start with nickel 2 plus. I'm writing the electronic configuration of nickel 2 plus. The electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. This is the electronic configuration of nickel. Since it is 2 plus, 2 electrons will be eliminated from 4s. So 3d is having 8 electrons now. 3d is having 8 electrons. 3d is having 8 electrons. Okay. So now we can draw the orbital diagram. We can draw the orbital diagram. It will be like 1, 2, 3, 4, 5, 6, 7, 8. Okay, 6, 7, 8. This will be the orbital diagram. Okay. So for nickel, this will be the orbital diagram. And you know, in the question it is mentioned that it should be low spin and octahedral. If it is octahedral, there are two possibilities. Either it will be D2sp3 or it will be sp3d2. If it is D2sp3, it will be low spin. Low spin. It will be if it is sp3d2, it will be high spin. High spin. Okay. But in the question it is given that it is low spin and octahedral. So it should be D2sp3. The hybridization, since it is, since the compound is low spin and octahedral, the hybridization should be D2sp3, because in D2sp3 we are using the inner d orbitals, not the outer one. We are using inner d orbital. Okay, so the hybridization should be D2sp3. That means from this nickel we have to take 2 d orbitals. But it is very much clear that if the ligand is strong, it will undergo pairing, right? Even after pairing, you will get a d orbital like this: 1, 2, 3, 4, 5, 6, 7, 8. Only one d orbital is left. So only one empty d orbital is possible from this nickel 2 plus ion. Okay, only one empty d orbital is possible. If only one is possible, then how can we obtain this hybridization? If you want D2sp3 hybridization, you need 2 d orbitals, right? But even after pairing, nickel 2 plus is having only one empty orbital. Okay, so it is not possible. For nickel 2 plus, even after pairing, it is having only one d orbital, Okay, so that's it. So assertion is correct. Low spin octahedral complex of Na2 plus ions are not known. It is not possible. What is the reason? Inner 2 empty orbitals are not available. That is also right. There will not be 2 d empty orbital. There will not be 2 inner empty orbitals. That is also right. So both assertion and reason are correct, and reason will be the correct explanation of assertion. That's it. Okay, so that's it. Is there any doubts? We finished most, we discussed most of the topics from the chapter. Okay. Yes, good. Anyway, I hope you enjoy it, and thank you so much. Okay.